data center is basically a huge building filled with computers. These machines run the apps, videos, payments, cloud storage, and artificial intelligence tools we use every day. They are normally kept in carefully controlled rooms, far away from rain, dust, and salt water. So the idea of sealing those computers inside a metal capsule and lowering them into the ocean sounds almost reckless. But engineers are not putting servers underwater because computers like the sea. They are doing it because computers create heat, and removing that heat is becoming one of the hardest parts of building the digital world. In this video, we are going to answer 4 simple questions. Why do data centers become so hot? How can the ocean help cool them? Why might sealed underwater servers fail less often? And most importantly, when does this idea make sense? And when is it just an expensive complication? The first thing to understand is that the cloud is not really a cloud. Every photo you back up, every movie you stream, and every answer generated by an AI system is processed by physical machines somewhere in the world. Those machines use electricity, and almost all of that electricity eventually becomes heat. A single laptop can become warm during a heavy task. Now place thousands of much more powerful computers together, run them day and night, and pack them tightly into rows. The result is not just a room full of technology, it is a giant source of heat. If that heat stays inside, the computers slow down, parts wear out faster, and the system may shut itself off to avoid damage. So every data center is doing 2 jobs at once. One part performs the digital work. The other part keeps carrying the heat away. That second job can require fans, pumps, cooling equipment, water, and a large amount of electricity. In some places, the computers are not the only problem. The local power grid, water supply, or available land may already be under pressure. This is why the growth of artificial intelligence matters. AI does not float invisibly in the air. It runs on powerful chips inside real buildings, and those chips can produce a great deal of heat in a very small space. The more computing we demand, the more difficult the cooling problem becomes. Now the ocean begins to look useful. Water can carry heat away much more effectively than air. Ocean temperatures also tend to change more slowly than the temperature above the surface. Engineers can use that stable environment as a large, natural place to release heat. But the seawater never touches the computers. The servers remain dry inside a strong, sealed metal container. Cooling liquid moves through the racks, collects the heat, and carries it toward the wall of the container. The heat then passes into the surrounding seawater. Power and internet connections travel through protected cables back to shore. The simplest way to picture it is this: the computers sit inside a dry metal shell, while the ocean acts like the outside of a very large refrigerator. That does not make the cooling free. Pumps still need power. The container must survive pressure, corrosion, and years of contact with seawater. The cables must remain protected. But the ocean may reduce the need for some of the large cooling systems used on land. It may also reduce the amount of fresh water needed at the site. That can be important near growing coastal cities, where land is expensive and fresh water may already be shared by homes, farms, and industry. So the first possible advantage is clear. The ocean may help remove heat while reducing pressure on land and fresh water. The second advantage is not about cooling. It is about how the data center is built. A normal data center is often a major construction project. The building, power system, cooling system, security, and computer equipment all have to come together at the same location. An underwater system can be built more like a large piece of industrial equipment. The computers and cooling hardware are assembled inside a factory. The complete unit is tested, sealed, transported to the coast, connected to cables, and lowered into position. In theory, this allows an operator to add new computing capacity one module at a time, instead of building one enormous campus from the beginning. That sounds faster and more flexible, but lowering heavy equipment into the sea still requires ships, cranes, skilled crews, suitable weather, and careful planning. The factory work may become simpler, while the marine work becomes harder. There is also a reason to place computing near the coast, even before cooling enters the conversation. A large part of the world's population lives near the sea. Putting servers closer to a major city can shorten the distance that some data must travel. For email or ordinary web browsing, the difference may be too small to notice. For cloud gaming, factory control systems, or services that must react almost instantly, even a small delay can matter. The important point is not that underwater computers are magically faster. It is that they can sometimes be placed close to the people, networks, and energy sources that need them. That last part, energy, may become one of the strongest reasons to take the idea seriously. Offshore wind farms generate electricity at sea. Normally, that electricity has to travel through large cables back to land before it can be used. An underwater or offshore data center could use some of that electricity nearby. The computers would consume the power, and their useful output would travel away as data through a much thinner fiber optic cable. Instead of moving all the electricity to the computers, some of the computers could move closer to the electricity. This is still an emerging idea, not the new standard for the entire industry. Microsoft helped prove that the basic concept could work through Project Natick. In 2018, the company lowered a sealed data center module to the seafloor near Scotland's Orkney Islands. The module contained hundreds of servers and remained underwater for about 2 years. When it was brought back to the surface, the surprising result was not simply that the computers had survived. The underwater servers had failed much less often than a similar group on land. At first, that sounds as if the ocean somehow made the computers stronger. It did not. The likely explanation was the calm, sealed environment inside the container. The air had been replaced with dry nitrogen, which is less reactive than normal air. The temperature and humidity stayed stable, dust could not enter, and no technician opened the doors, moved cables, or accidentally disturbed a working system. The computers may have become more reliable underwater, partly because people could not touch them. That is a fascinating result, but it immediately creates a problem. If nobody can enter the module, nobody can repair a broken server. On land, a technician can walk into the building, replace a failed part, and return the machine to service. Underwater, a broken server may remain broken until the entire container is brought back to shore. Recovering it could require a ship, specialized crews, good weather, and much more planning than an ordinary repair. The same sealed capsule that protects the machines also locks the engineers outside. To make this workable, the system must be designed so that a few failed computers do not matter very much. There must be extra capacity. Important connections need backup routes. Software must move work away from a damaged machine and onto one that is still operating. In other words, the operator does not treat every server like a device that must be repaired immediately. The whole module is treated as a group. Some machines may fail, while the rest continue working. Later, during a planned service period, the complete module can be recovered, repaired, upgraded, or recycled. This approach may work well for common cloud tasks that can easily move between many machines. It is much less attractive when the hardware needs frequent changes or constant physical access. And the ocean creates problems that do not exist inside an ordinary building. Saltwater slowly attacks many materials. Pressure tests every seal. Marine organisms can grow on the outside of the container. Anchors, fishing equipment, strong currents, storms, or movement on the seabed can damage cables and structures. None of these problems is completely new. Offshore wind farms and underwater communication cables already face many of the same conditions. Engineers know how to use protective coatings, strong connectors, careful monitoring, and proven marine construction methods. But knowing how to manage a danger does not make the danger disappear. It only makes the risk easier to predict. Then we reach the environmental question. It is easy to hear the phrase natural ocean cooling and assume that the heat simply goes away. It does not. Every computer still produces heat, and an underwater data center releases that heat into the surrounding water. A small module in cold, fast-moving water may cause only a limited change nearby. A large group of modules in warmer or slower water could have a much greater effect. That is why the location matters so much. Engineers need to measure the water temperature, currents, and local marine life before installation. They also need to keep measuring after the system begins operating. A project that works safely in one part of the ocean may not be suitable in another. The same is true for the full environmental cost. An underwater system may save freshwater, but ships are needed to install and recover it. The container must be manufactured, cables must be laid, and the electricity still has to come from somewhere. If the servers run on high-carbon electricity, efficient cooling alone does not make the project clean. Cooling is only one part of the story. The energy source, construction, maintenance, and final removal all matter. Security also changes underwater. A sealed capsule has no front door, no loading dock, and no employee walking past the machines. That makes some types of physical access more difficult, but the system still depends on power cables, internet cables, equipment on shore, and software control. If a major cable is cut, the servers may still be working perfectly while becoming unable to communicate or receive power. The ocean creates a barrier. It does not make the system impossible to attack or damage. So, after all these advantages, why not move every data center underwater? Because the ocean only helps when several conditions come together. The location needs strong demand for computing, limited or expensive land, a suitable seabed, reliable cable connections, access to marine engineering, cool moving water, and preferably, a nearby source of low-carbon electricity. When those conditions exist, the seafloor may offer real advantages. When they do not, the ocean becomes a very expensive place to put computers that would have been easier to build, repair, and expand on land. A land-based data center can also be highly efficient. It may sit beside a power plant, use cold outside air, connect to several network routes, or send its waste heat into nearby homes and buildings. There is no single perfect location for every data center. The better question is not, is underwater better than land? The better question is, which location uses the least energy, water, land, and money for the job that needs to be done? That brings us back to the title. Are data centers moving under the ocean to save our digital future? A few projects are moving in that direction, but the entire internet is not heading below the waves. Underwater data centers are still a specialized solution. They may be useful near coastal cities, offshore wind farms, and places where land, freshwater, or cooling capacity is limited. They may also show that sealed, factory-built computing systems can operate with fewer human mistakes. But they will only succeed when the savings in cooling, land, and water are greater than the cost of marine construction, difficult repairs, cable protection, and environmental monitoring. The real lesson is larger than the ocean. The digital world is physical. Artificial intelligence, cloud services, and online entertainment all depend on electricity, water, materials, cables, and real places on the planet. As computing demand grows, the future will not be saved by one dramatic idea. It will require more efficient chips, cleaner electricity, better software, smarter cooling, and different types of data centers designed for different locations. Underwater computing is one tool inside that much larger toolbox. Its greatest value may be that it forces us to ask a question the technology industry could once ignore. Where should computing happen? Once energy, water, land, and the environment become part of the calculation? The answer may sometimes be beneath the ocean. In many other cases, it will remain firmly on land. Subscribe for more clear, visual explanations of the technology and infrastructure shaping what comes next. Thanks for watching, and I'll see you in the next video.